What if the universe has no boundary you could ever reach, yet it keeps getting larger everywhere at once? What hidden rule of nature lets reality stretch without a rim to push against? And what would you see if you could ride the light that left the first dawn and ask it whether an edge exists at the farthest horizon you can never cross? The night sky looks still to the naked eye, yet careful measurements reveal that galaxies are receding from one another in a pattern that matches a smooth stretching of space itself rather than motion through a pre-existing emptiness, which means there is no central explosion to point back to, only a change in the scale of distances that rewrites how far apart things are with every passing moment. When astronomers describe this growth, they speak of a scale factor that multiplies all large distances. So if the scale factor doubles, then every separation between far-flung clusters doubles as well, while local islands bound tightly by gravity, such as our galaxy, remain held together because their internal pull overwhelms the gentle stretch of the cosmic fabric. This picture was first clarified when a relation between distance and recession speed was found in the light of distant galaxies, where spectral lines were shifted toward longer wavelengths in proportion to how far the light had travelled, implying not a wind pushing galaxies outward, but a uniform expansion that carries even the photons themselves to redder colours as space elongates under them. If the universe has no edge, that does not mean it must be infinite, since geometry allows a surface without boundary yet with finite extent, like the surface of a sphere that has no last point you could stand upon, and cosmology extends this intuition into 3 dimensions where space can be flat, open, or positively curved while still lacking any literal border where the cosmos would stop. On the larger scales, the cosmos appears statistically uniform in every direction and at every place, a principle called cosmic homogeneity and isotropy that does not erase local variety but tells us that if you average over hundreds of millions of light years, the patterns look the same, which is precisely the condition under which an edgeless expansion makes coherent sense. General relativity supplies the engine for this behaviour by replacing gravity as a force with the curvature of space-time caused by matter and energy, so that when you fill a nearly uniform space with a nearly uniform energy density, the natural solution is a metric that either expands or contracts, and our observations clearly show the expanding branch rules the present epoch. The evidence for this story is not a single clue, but a network of mutually reinforcing signals, beginning with the cosmic microwave background, which is the cooled afterglow of the hot early universe, a bath of microwave light arriving from every direction with tiny temperature ripples that map the primordial seeds of galaxies and confirm a space that has been stretching for billions of years. Those ripples are frozen sound waves called baryon acoustic oscillations that left a preferred scale in the distribution of galaxies, a kind of standard ruler spread across the cosmos which we can measure at many epochs. And when we compare that ruler to the redshifts of galaxies, we see exactly the pattern expected if distances have grown in the way predicted by the equations of an expanding universe. Supernova explosions of a particular type serve as standard candles whose intrinsic brightness can be inferred from the way their light curves behave, and when astronomers plotted many such supernovae across cosmic time, they found that the expansion has not only persisted, but has accelerated in the last several billion years, pointing to a pervasive component of energy that does not thin out with expansion. We call that mysterious component dark energy as a placeholder for our ignorance, and the simplest explanation that fits the data is a constant energy density of empty space itself, often described by the cosmological constant in the field equations, which acts with negative pressure so that as space grows its influence does not dilute, leading to acceleration without a need for any cosmic wind. If you ask how there can be no edge while everything moves apart, consider a baking raisin bread in which the dough is like space, and the raisins are like galaxies that ride along, where from any raisin you would see the others recede with speeds roughly proportional to distance. Yet there is no special raisin at the centre of the loaf, and there is no crust that marks the end of space itself. The observable universe defines a practical horizon, not an edge of existence, because light has a finite speed and there has been a finite time since the hot beginning, so we can only receive signals from within a sphere about 46 billion light-years in radius today, but beyond that lies more universe that we cannot see yet, possibly with the same statistics we measure locally. Inflation is a proposed era of extremely rapid expansion at a very early time, which smooths and flattens the cosmos while stretching quantum fluctuations to astronomical scales. and it explains why distant regions share the same temperature and why the primordial ripples look almost scale invariant with slight deviations that match precision measurements of the cosmic microwave background. If inflation happened, then the part we observe is only a small patch of a much larger entity, and depending on the overall curvature, the full space may be extremely close to flat and yet still edgeless, or it may be curved in a way that closes on itself while exceeding our horizon by many factors, leaving the question of finiteness unsettled, but the absence of a border entirely consistent. The expansion is not a motion through a higher dimensional container, rather it is a change in the metric that defines the distances between co-moving points, so embedding diagrams that show a balloon surface or a stretching grid are helpful for intuition, but should not be mistaken for evidence that space floats within a larger external arena that sets a physical boundary. Galaxies do not feel a friction against space as they recede, which is why their ancient light still reaches us though its wavelength is stretched, and the energy of those photons diminishes in a way that is exactly accounted for by the conservation laws within an expanding geometry where global energy bookkeeping is subtle, but local physical laws remain perfectly intact. On small scales, gravity, pressure, magnetic fields, and feedback from stars and black holes weave structures that resist the global trend. So while the universe doubles its large-scale distances over vast intervals, the Milky Way keeps its stars in orbit, the solar system remains tightly bound, or even the space within your room is utterly unaffected by cosmic expansion. The early universe was hot and dense enough to forge the lightest nuclei during a period called Big Bang nucleosynthesis, whose leftover abundances of hydrogen, helium, and lithium match what we observe in primordial environments, providing an independent fingerprint of a hot beginning that expands and cools in a way consistent with everything else we measure about the large-scale cosmos. As the universe expanded and cooled further, electrons combined with nuclei to form neutral atoms, letting light travel freely for the first time, and that decoupled radiation is the cosmic microwave background we observe today with exquisite clarity, a nearly perfect blackbody spectrum with tiny anisotropies that trace the initial conditions for the growth of all later structure. The growth of structure from those initial ripples follows the pull of dark matter, which interacts by gravity but not by light, enabling halos to form that gather gas which cools and condenses into stars and galaxies, while the overall expansion sets the stage on which this hierarchy unfolds, proving that a universe can be edgeless yet dynamically rich, with local knots that defy simple uniformity. Distance in a dynamic universe is not a single concept but many related measures, such as co-moving distance that factors out expansion, luminosity distance that links brightness to geometry, and angular diameter distance that ties apparent size to the history of the scale factor, and each of these plays a role when astronomers turn observations into precise constraints on cosmic parameters. When people imagine an edge, they often picture a cliff where existence ceases, but the equations tell us that space can be finite without borders like the surface of a globe, or infinite yet still without any special outer rim, and in either case the expansion is a local rule applied everywhere, not a pushing from outside but an intrinsic change of the metric between nearby points. The present acceleration means that very distant galaxies will eventually slip beyond our event horizon, making their future light unable to ever reach us no matter how long we wait. And this cosmic isolation offers a melancholic forecast where only the nearest group of galaxies remains visible in the far future, while the rest fade into irretrievable darkness as space continues to accelerate. Yet right now we inhabit a moment rich in information, because we can still see the afterglow of the beginning. We can map the large-scale web traced by galaxies and gas. We can weigh the ingredients of matter and radiation of dark energy. And we can test gravity itself on the grandest stage by comparing predictions to a deep archive of measurements that keeps growing in detail. The lambda-cold dark matter model provides a simple baseline that captures the expansion history and structure growth with only a few parameters, describing a universe filled mostly with dark energy and dark matter, plus a smaller portion of ordinary atoms. Yet this success is not the end of inquiry because we still do not know the microphysical identity of either dark component. Precision surveys of galaxy clustering, weak gravitational lensing, and the pattern of the cosmic microwave background polarization keep tightening our estimates of those parameters, while searches in laboratories and underground detectors look for dark matter particles, and theoretical work explores whether dark energy is a cosmological constant or a more dynamic field that changes gently over time. The absence of an edge becomes intuitive when you accept that coordinates are a choice rather than a substance, so you can draw a grid that wraps smoothly on itself or extends forever, and the physics cares about the local relationships between events encoded in the metric and the geodesics that particles follow, not about an absolute outer wall that would break the very symmetries the data support. If you could travel impossibly fast along a straight path in a positively curved finite universe, you might return to your starting point with no boundary crossed, though your journey would take longer than the age of the cosmos because the path is immense, and expansion keeps adding distance. A thought experiment that highlights how edgeless does not mean trivial or easily navigated. In a spatially flat universe, the sum of the interior angles of a giant triangle drawn by light beams is 2 right angles, a fact tested by measuring the apparent size of features in the cosmic microwave background, and the results point to near exact flatness within our horizon, while leaving open the possibility that on scales we cannot access the global topology still wraps without edges. Every time we calibrate a standard candle or a standard ruler, we refine the map that links redshift to distance, and this has revealed mild tensions in how different methods infer the present rate of expansion, prompting intense checks of data and models that are a healthy sign of science at work, because the resolution will either teach us new astrophysics or sharpen our understanding of systematics. Even the language we use can mislead, because the phrase Big Bang evokes an explosion into space, while the modern view describes an everywhere expansion of space. So the history is not a fireball erupting from a point, but a hot, dense state filling all of space that cools and rarefies as the scale factor grows, with no outer emptiness required to receive the blast. The notion of nothing outside the universe confuses because our intuition is tied to objects embedded in larger rooms. Yet space is the stage itself, not a thing that sits within a bigger hallway. So asking what lies outside can be like asking what is north of the North Pole, a question that points to the limits of a metaphor rather than to a literal boundary awaiting discovery. From this vantage, the original question becomes sharper, not whether space needs an edge in order to expand, but how the content of the universe curves space-time to yield a scale factor that evolves in time, and our task is to measure that evolution with many independent rulers and candles and clocks until our description becomes as precise as the phenomena deserve. For a viewer seeking practical images, remember that the expansion barely touches your daily world, because bound systems are shielded by their own gravity or cohesive forces, so you will not see rulers grow or rooms enlarge. Yet the photons from a distant galaxy carry the story in their stretch, and when you look deep with a powerful telescope, you're looking back across a history written in lengthened light. If space is edgeless, the horizon still sets a limit on what can be known, and this limit is not a failure, but a feature that gives physics a domain in which predictions can be tested, since we can compute how structures should cluster, how background light should fluctuate, and how gravitational lensing should distort images, then compare those predictions with the sky we actually map. As the story continues, the expansion will render the universe colder and emptier on average, while stars burn their fuel and structures slowly change. But for a very long time, our local group of galaxies will remain together under mutual gravity, preserving a pocket of richness amid the broader thinning, which means the cosmic stage is both vast and intimate depending on the scale you choose. So when you wonder how something without an edge can grow, you're really asking how geometry responds to energy and pressure, how initial conditions led to the structures we see, and how the equations that govern space-time translate into the images you can capture with a camera, all of which is a journey we can take together through observations that are concrete and theories that are testable. If you follow the light from the first atoms to the present day, you trace a timeline that requires no outer border, only the steady march of the scale factor and the interplay of gravity and pressure, and the small ripples that formed galaxies now whisper to us through faint background patterns, telling the same tale in multiple dialects of the cosmos that we can learn to read. The answer hides in plain sight across many measurements that all point to one cohesive narrative, that space is a self-consistent fabric whose distances evolve with time according to the energy within it, that there is no cosmic shore to crash upon, and that the right question is not where the edge lies, but how the fabric changes, what that change reveals about the deep ingredients of reality. Keep that question in your mind as we move deeper into the evidence, because the deeper we look, the more the universe rewards patience with clarity, and in the end the absence of an edge is not a mystery at all once you see that expansion is an internal rule rather than an external push, a rule that turns the whole cosmos into a dynamic stage where distance itself is an actor. Before we step forward, it helps to take stock of what we established, that expansion is not motion through an outside, but a change in the metric that scales distances, that horizons limit what can be known without implying a border, that dark energy drives late-time acceleration, that dark matter seeds structure, and that multiple independent observations knit these ideas into a single coherent tapestry. To avoid repeating earlier ground, we will now press into the machinery that turns ideas into numbers by tracing how the Friedmann equations arise from general relativity for a homogeneous and isotropic universe, how they relate the scale factor to the densities of radiation, matter, curvature, and dark energy, and how each component controls the tempo of expansion across different eras. The first Friedmann relation ties the square of the expansion rate to the total energy density minus a curvature term, so when radiation dominated the early cosmos, expansion was swift because energy density scaled strongly with the scale factor. Later matter took over and slowed the growth, while in our epoch a nearly constant vacuum energy bends the curve upward to yield acceleration. The second Friedmann relation describes how the expansion rate changes with time by including pressure as well as energy density, showing why a component with negative pressure like vacuum energy pushes the expansion to accelerate, which is not a push from outside space but a response of geometry to a peculiar equation of state residing everywhere at once. Parameter estimation enters when surveys measure the redshift to distance relation with standard candles, standard rulers, and gravitational lenses, then fit the results to the model space spanned by matter density, baryon fraction, dark energy equation of state, curvature, and the current expansion rate known as the Hubble constant, while carefully tracking systematic uncertainties that could bias inference. To strengthen the story, we lean on consistency relations, such as the reciprocity between angular diameter distance and luminosity distance that follows from photon number conservation in a metric theory, which allows cross-checks between supernova brightness data and baryon acoustic oscillation size measurements across the same range of redshift without relying on a single method. Another test is the Tolman surface brightness relation, which predicts that surface brightness of identical objects dims with the fourth power of 1 plus redshift in an expanding universe, a striking signature verified in galaxy samples that would not appear in a static tired light scenario, reinforcing that redshift stems from expansion rather than from cumulative interactions with intervening material. We can even ask how expansion reveals itself in principle through the redshift drift, a tiny change in the redshift of distant objects observed across human decades, which future ultra-stable spectrographs could detect to provide a direct real-time movie of the changing scale factor, independent of standard candles or rulers and immune to many calibration pitfalls. Standard sirens from gravitational waves add a new rung to the cosmic distance ladder, because the waveform amplitude and frequency evolution of inspiraling binaries encode an absolute luminosity distance without needing to know the intrinsic brightness. When a counterpart provides redshift, we obtain an expansion rate measurement that sidesteps many traditional uncertainties. The pattern of weak gravitational lensing, a gentle shearing of galaxy shapes by intervening mass, offers sensitivity to both geometry and the growth of structure, so by mapping shear correlations across the sky and across redshift slices we test whether the same expansion history that fits distance indicators also predicts the correct rate at which matter clusters under gravity. Large neutral hydrogen clouds imprint a forest of absorption features in quasar light known as the Lyman alpha forest, a tracer that acts as a cosmic seismograph for density fluctuations on intermediate scales, letting us reconstruct the matter power spectrum at high redshift and compare it to predictions from the initial fluctuations stretched by inflation and evolved under expansion. The epoch of rayonization, when the first luminous sources ionize the intergalactic medium, leaves signatures in the polarization of the cosmic microwave background and in the damping of small-scale power, while the future promise of 21-centimeter cosmology could map the three-dimensional history of that transition, turning a foggy period into a charted timeline tied to expansion. We also probe topology without repeating earlier analogies by searching for matched circles in the sky within the cosmic microwave background, a geometric fingerprint that would arise if space wraps around on scales comparable to the horizon, and although current data find no compelling evidence, the method exemplifies how edgelessness can still carry global structure awaiting discovery. Curvature constraints emerge from comparing the angular size of acoustic features to their expected physical scale, revealing that spatial curvature within the observable patch is very close to zero. Yet this near flatness does not erase the possibility of non-trivial global connectivity on unobservably large scales, keeping the question of ultimate size open while edges remain unnecessary. Attention then turns to the so-called Hubble tension, the mild but persistent mismatch between the Hubble constant inferred from early universe fits that rely on the cosmic microwave background and baryon acoustic oscillations, versus late-time direct measurements that use calibrated supernova and distance anchors, a discrepancy that motivates scrutiny of systematics and exploration of subtle new physics. Whatever the resolution, the exercise underscores a theme we will not repeat but deepen, that a robust cosmology requires a web of interlocked checks, where geometry, growth, and relic backgrounds all agree, because only a mutually consistent picture earns the right to claim there is no hidden edge requiring exotic explanatory scaffolding. Perturbation theory on an expanding background describes how tiny initial fluctuations evolve, with modes growing under gravity while pressure and radiation drag resist collapse, leading to a transfer function that shapes the modern power spectrum. So galaxy surveys essentially read a fossil record of how expansion and content guided the assembly of structure from whisper to chorus. Nonlinear evolution demands numerical simulations that follow billions of particles under gravity and hydrodynamics, tracking gas cooling, star formation, feedback from supernovae and black holes, magnetic fields, and radiative transfer, then comparing synthetic skies to observations to ensure the same expansion history that fits distances also yields believable galaxies within their dark halos. Voids, the large underdense regions in the cosmic web, provide complementary information because their shapes and alignments are sensitive to geometry, and the growth rate, enabling tests through the Alcock-Pogsinski effect, which compares observed anisotropy to the expectation from the assumed expansion, creating yet another geometric lever arm independent of standard candles. Peculiar velocities, the deviations of galaxy motions from pure Hubble flow caused by gravitational pulls of nearby structures, let us measure the growth parameter by correlating velocities with density, giving a dynamical crosscheck that does not rely solely on distances, but on how mass literally drags galaxies through the expanding stage. The integrated Sachs-Wolf effect arises when photons climb out of time, evolving gravitational potentials in an accelerating universe, imprinting a subtle correlation between large-scale temperature fluctuations in the cosmic microwave background and nearby large-scale structure, a signature that speaks directly to the presence of dark energy affecting geometry across expansive vistas. Secondary anisotropies from the Sunyaev-Zeldovich effect, where hot electrons and clusters scatter background photons, give an independent handle on growth because the abundance of massive clusters over time depends sensitively on expansion and matter content, turning galaxy clusters into thermometers and yardsticks in a single astrophysical package. At the opposite extreme of scale, laboratory physics constrains cosmology when precise measurements of particle properties feed into early universe calculations, since the effective number of light neutrino species alters the expansion rate during nuclear synthesis and recombination, leaving fingerprints in element abundances and the detailed shape of the microwave background spectrum. Thermodynamics meets geometry at cosmic horizons, where an accelerating universe approximates de Sitter space with an associated horizon temperature and entropy, raising deep questions about information in an ever-expanding stage, while the cosmic no-hair conjecture suggests that expansion with positive vacuum energy erases memory of initial anisotropies, leaving a smooth attractor state. Redshift space distortions, the apparent squashing or stretching of clustering patterns along the line of sight, caused by peculiar motions, turn galaxy redshift surveys into dynamical laboratories that simultaneously probe expansion through geometry and test gravity through the rate at which structure forms, allowing checks against modifications that mimic dark energy at the background level. Time delay cosmography and strongly lensed quasars provides another distance measure, because different light paths through a lensing galaxy produce multiple images that flicker with delays set by geometric distances and gravitational potentials, enabling an independent estimate of the Hubble constant when the mass distribution of the lens is carefully modelled. Cosmic chronometers use the differential ages of passively evolving galaxies to estimate the derivative of redshift with respect to time directly, furnishing a measurement of the expansion rate as a function of redshift that does not involve standard candles or rulers, thereby adding yet another strand to the weave of independent evidence. To ensure that edgelessness is not a rhetorical trick, we also examine inhomogeneous models that attempt to reproduce observations without dark energy by placing us in a large cosmic void, but precise data on the isotropy of the cosmic microwave background, the kinematic Sunyaev-Zeldovich effect, and supernova anisotropies severely constrain such scenarios, preserving the homogeneous expansion picture. Back reaction, the idea that small-scale clumpiness could significantly alter large-scale expansion when averaged, has been investigated with exact solutions and numerical experiments, yet the prevailing consensus is that its effect on the global scale factor is too small to replace dark energy, though it remains a subtle reminder that averaging in general relativity is non-trivial. We can connect cosmic dynamics to local laboratory clocks through dimensionless numbers, since variation in fundamental constants would shift atomic spectra in distant quasars and alter Big Bang nucleosynthesis predictions. So the absence of compelling evidence for variation reinforces that the same physics rules from early times to now, while expansion proceeds as a geometric evolution rather than a change in laws. The reionization history inferred from polarization and from the faint glow around distant galaxies informs the timeline of star formation, which in turn controls the production of heavy elements and dust, thereby influencing how we calibrate standard candles across redshift, a chain that must be modelled with care to keep the measure of expansion free from hidden biases. Closer to home, the solar system offers a quiet confirmation by refusing to participate, since orbital dynamics, planetary radar ranging, and atomic scale physics show no secular drift consistent with cosmic expansion at bound scales, which is exactly what the theory predicts once local gravity overpowers the minute cosmic stretching. Even the background light that accumulates from all galaxies, the extragalactic background light, plays a cosmological role because high-energy gamma rays from distant blazars are attenuated by pair production on this sea of photons, allowing us to gauge cosmic star formation history and cross-check expansion-dependent models that predict how much light should have been made. As we refine surveys with wider fields and deeper exposures, attention to selection functions, completeness, photometric calibration, and redshift accuracy becomes paramount, because a small bias propagated across billions of objects can masquerade as a physical effect in the expansion history, reminding us that rigor in data handling is as vital as elegance in theory. Forthcoming facilities promise to turn rare probes into routine tools, from extremely large telescopes that can capture the faintest supernovae at high redshift, to radio arrays that map hydrogen across cosmic time, to space missions designed to tame systematics in weak lensing and supernova cosmology, each aimed at pinning down how expansion responds to the energy content with exquisite fidelity. Meanwhile, theory explores whether dark energy could vary slowly with time, whether gravity itself deviates from general relativity at vast distances, or whether subtle couplings in the dark sector could explain anomalies, each scenario forced to pass the gauntlet of distance measures, growth rates, lensing patterns, and early universe relics that jointly police the story of expansion. The most valuable habit we can bring to this question is the willingness to triangulate, to measure the same underlying geometry with many different tools that fail in different ways, so that concordance is meaningful rather than accidental, a practice that has already transformed the idea of an edgeless expanding universe from speculation into a quantitatively tested description. As cosmic time flows forward, the acceleration will make standard rulers appear to stall at a finite angular size while distant structures thin out. But within our gravitationally bound local group, a rich sky will persist, ensuring that even as the average density falls, the immediate cosmos remains a laboratory where stars evolve, planets orbit, and physics continues indifferent to the vast thinning outside. From quantum fluctuations magnified at the beginning to the nearly empty expanses of the distant future, the common element is that distances change according to equations that respect symmetry and conservation in curved space-time, meaning that growth without edges is not an exception to a rule, but the rule itself applied everywhere, a rhythm set by energy and pressure rather than by borders. We can therefore frame the guiding curiosity with sharper edges of thought rather than literal edges of space, asking which precise combination of matter, density, dark energy behavior, and initial fluctuation spectrum best matches the full suite of data, because when that combination is found, it not only explains the past expansion, but predicts the future path along which horizons evolve. So the continuation of our story is not a repetition but an escalation, moving from metaphors to measurable consequences, from single probes to a lattice of cross-checks, and from a general assurance that there is no border to a detailed audit of how geometry evolves with content, which is the heartbeat of a universe that expands everywhere without ever needing an outside. Starting from the lattice of cross-checks already laid out, we lean into calibration because the path from raw light to precise distance is never straightforward. So the distance ladder is tied together by carefully interlocked rungs, where pulsating variable stars set local scales. Tip of the red giant branch stars extend that anchor to further galaxies, and Mesa orbits in circumnuclear disks provide geometric baselines that keep the entire structure honest. These anchors propagate to supernova luminosities with meticulous attention to metallicity, crowding, dust extinction, and photometric zero points, where a fraction of a percent in brightness translates into kilometers per second per megaparsec in the inferred present expansion rate, so astronomers design observing strategies that interleave filters, repeat fields, and cross-reference independent instruments to trap hidden biases before they masquerade as cosmic truth. Moving outward in redshift, we watch how baryon acoustic oscillation measurements sharpen through reconstruction techniques that reverse some of the blurring caused by nonlinear flows, restoring the primordial crest to a cleaner standard ruler, and when that ruler is compared across optical galaxy surveys, emission line maps, and quasar absorption fields, the same scale reappears with a patience that only the cosmos can maintain. Weak lensing, already introduced as a gentle shear of shapes, now becomes a tomographic tool when galaxies are sorted into redshift slices, because the cross-correlations of foreground mass with background distortions encode both geometry and the growth rate as a function of time, a double sensitivity that forces any viable model to pass tests in two different languages at once. To draw meaning from such delicate distortions, we must tame point spread functions, atmospheric seeing, detector nonlinearity, and intrinsic alignments where galaxy shapes respond to local tides, so analysts build forward models that stream from photons through pixels to measured ellipticities, validating every step with image simulations that mimic the sky so well they can fool their makers. Gravitational lensing also magnifies fluxes and alters number counts, a subtlety used to weigh large-scale structure via magnification bias, which complements shear by focusing on changes in apparent density rather than shape. And when combined with the cosmic microwave background lensing map derived from temperature and polarization deflections, the full three-dimensional scaffolding of matter begins to appear. The cosmic microwave background itself contributes beyond its first glow by carrying a polarization swirl generated when density ripples scatter light at recombination, and these patterns are then remixed by gravitational deflection into small non-Gaussian features whose detailed statistics let us weigh the sum of neutrino masses and test whether the initial fluctuations were as simple as nearly Gaussian quantum seeds. Neutrinos, nearly weightless, and once free streaming across the young universe, suppress growth on small scales in a way that fingerprints their collective mass, so galaxy clustering, cosmic microwave background lensing, and Lyman alpha forest power combine to turn a particle physics question into a cosmological measurement, narrowing the space in which new physics can hide. While the standard story treats dark matter as cold and collisionless, we can push that assumption by chasing signatures of warmth, self-interaction, or wave-like behavior, each of which imprints a different cutoff or core in the distribution of small halos, so surveys that count faint satellites, strong lensing anomalies, and low-mass galaxy rotation curves become laboratories for the invisible. Reionization then returns to the foreground through the promise of 21 centimeter intensity mapping, where neutral hydrogen gas acts as a backlight tracer across vast co-moving volumes, letting us watch ionized bubbles grow and percolate as the first stars and black holes ignite, while the same technique at later times maps the large-scale structure as an economical three-dimensional recorder of expansion. The Alcock-Pazinski effect we touched earlier becomes a sharper blade in these maps, because any mismatch between the assumed expansion history and the true one squashes or stretches clustering patterns along the line of sight relative to the sky. creating a purely geometric anisotropy that cares little about bias or luminosity, only about how we convert redshift and angle into distance. Peculiar velocities add yet another channel by revealing how gravity accelerates matter, which is observed as redshift space distortions in galaxy surveys, and by directly measuring coherent motions through distance indicators that bypass redshift itself, we can compare the inferred growth rate with the prediction from the same geometry that distances demand, a consistency test between the shape of space and the pull within it. Strongly lensed quasars continue to refine time delay cosmography, where improved adaptive optics imaging, stellar kinematic measurements of the lens galaxy, and flexible, yet physically motivated mass models shrink uncertainties, letting the relative delays between flickering images translate into distances, which in turn send an independent message about the present expansion rate. Cross-correlation is the quiet hero of this era, because independent maps carry complementary strengths and weaknesses, so correlating galaxy positions with cosmic microwave background lensing, or with radio intensity maps, or with maps of the thermal Sunyaev-Zeldovich effect, amplifies the shared signal while cancelling instrument-specific quirks, turning datasets into a chorus rather than a solo. Kinematic Sunyaev-Zeldovich measurements, where the motion of ionized gas imprints tiny temperature shifts on the background light, let us weigh flows on very large scales, transforming galaxies and groups into test particles that respond to gravity on the grandest stage. And by stacking many such systems, we can detect the streaming motions that theory predicts for a universe with our measured contents. Turning to topology without restarting the tale, we use searches for repeated patterns not only in the cosmic microwave background, but also in catalogues of rare objects, because a multiply connected space could produce ghost images of the same structure at different angles and redshifts, a speculative but testable idea that keeps the door open for global shape without any literal boundary. As measurements tighten, we confront cosmic variance, the statistical limit that arises because we observe a single universe with a finite number of large-scale modes, which means some uncertainties cannot be beaten by more photons alone, so clever strategies like measuring multiple traces of the same density field can cancel sample variance and squeeze fresh information from the same sky. The philosophy of inference matters as much as the instruments. Therefore, analysts embrace hierarchical models that propagate uncertainties from raw counts through calibrations into cosmological parameters, while openly publishing simulated challenges where teams attempt to recover hidden truths from controlled datasets, a practice that forges trust before the numbers touch the deeper questions. Laboratories on Earth feed back into this web by pinning down atomic transition probabilities, detector linearities, and absolute flux scales, because cosmology at the percent level is inseparable from metrology at the percent level, and when careful calibration of spectrographs or photometers shaves a small systematic, the benefit echoes across redshift ranges that together decide how fast space grows. With this groundwork, we can push on the physics of dark energy in a way that does not repeat earlier descriptions, by asking whether the equation of state parameter is exactly -1 or deviates slightly with time, and by checking if gravity on large scales modifies the relation between the growth rate and the expansion history, because the pair of tests together can expose masquerades that fool either one alone. If gravity were altered at huge distances, it would change the slip between the two gravitational potentials that lens light and accelerate matter, a subtle indicator that reveals itself in joint analyses of lensing, galaxy motions, and the integrated Sachs-Wolf correlation. So even without touching a particle detector, we turn the whole sky into a precision apparatus for the law that binds it. Primordial non-Gaussianity, the slight preference for certain shapes of three-point correlations in the initial fluctuations, would betray interactions during the earliest headlong growth, and it leaves a late time signature by biasing how galaxies populate halos on the larger scales, meaning that an edgeless expansion can still carry a fossil whisper from epochs when wavelengths were smaller than atoms. Gravitational-wave standard sirens step into this tapestry with increasing confidence as detectors grow more sensitive, because merging neutron stars in distant galaxies produce an absolute distance scale, while any electromagnetic counterpart delivers redshift. And even when counterparts are absent, statistical associations with galaxy catalogues can still trace the expansion curve through cosmic time. At the thermal end of the spectrum, the abundance and internal structure of galaxy clusters provides another lever, since a universe with more matter or less repulsive energy will produce a different growth trajectory, so X-ray temperatures, thermal Sunyaev-Zeldovich decrements, and weak lensing masses meet in joint fits that trade individual complexities for ensemble power. Voids continue to earn attention because their expansion is less impeded by gravity, making them sensitive barometers of the background evolution, and their shapes offer a clean version of the Alcock-Paksinski test, while their interiors amplify subtle relativistic effects, turning emptiness into a measuring stick carved out of the web's negative space. To keep the narrative flowing, consider how time itself becomes unobservable through redshift drift, where decade-long stability in spectrographs would reveal tiny changes in the wavelengths of distant absorption lines, providing a direct movie of acceleration without standard candles or rulers, a minimalist yet profound confirmation that the scale factor is truly changing now. Cross-checking the origin of dimming is vital, so the Tolman surface brightness test continues to be applied in new bands and to new populations, while near-infrared observations mitigate dust and evolution, ensuring that the signature of the fourth power dimming with redshift remains a geometric verdict rather than a story about tired photons or hidden soot. Large photometric surveys add billions of galaxies but face the challenge of estimating redshifts from colours rather than spectra, so machine learning and template fitting are trained on deep spectroscopic samples, with special attention to the tails of the distribution where catastrophic outliers live, because a few misplaced galaxies can ripple into spurious inferences about expansion. Meanwhile, intensity mapping in multiple lines such as carbon monoxide and ionized carbon promises to capture aggregate emission from otherwise invisible galaxies, complementing traditional resolved catalogues and bringing a denser sampling of the three-dimensional field that tracks expansion through the same standard rulers while sidestepping selection thresholds that bias the luminous. The theme that emerges without retreating to earlier ground is that geometry, growth and relic radiation are not separate stories, but different camera angles on one unfolding process, which is why joint likelihoods that combine all probes often yield tighter and more reliable answers than any single method, provided their covariances and shared systematics are modelled with humility. When we project forward, we find that acceleration gradually hides distant structures behind an event horizon while leaving local bonds intact, but even in that far future, the imprints we record now will still be legible to any patient observer because the pattern of abundances, the web of weak lensing, and the fossil background of microwave light carry an enduring account of how distance itself evolved. This durability of evidence motivates meticulous archiving, uniform reprocessing of older images with modern pipelines, and open data releases that invite independent checks, since the question that began with a paradox about edges becomes a mature enterprise where certainty grows not by assertion, but by the convergence of many transparent analyses that can be rerun by any capable hand. Beyond measurements, conceptual clarity continues to sharpen as we examine energy conservation in curved spacetime more carefully, recognizing that global energy bookkeeping loses meaning when the stage itself is dynamic, yet local conservation encoded in the stress-energy tensor holds perfectly, which reframes the redshifting of photons as geometry at work rather than as energy disappearing into nothing. Entropy flows enter the picture with horizons that carry temperatures and entropies, so thermodynamic analogies hint that acceleration has an arrow of time, not only in the cooling of matter, but in the information content of what can ever be observed, and these ideas remain testable at a philosophical distance by the way structure formation slows while the background keeps thinning. Even as we refine parameters, we keep an eye open for surprises like deviations in the parity of polarization patterns, hints of cosmic birefringence, or anomalies on the largest angular scales, because an edgeless expanding universe is a framework that can host small cracks where new physics peers through, and progress comes from building experiments brave enough to look. To stay honest about flow rather than repetition, we now turn to the practical choreography of inference, where catalogues, covariance matrices, and end-to-end simulations dance together, because only by stress-testing pipelines against synthetic skies can we ensure that the elegant equations of geometry survive contact with the imperfect texture of real data. Survey strategy itself becomes a cosmological parameter when choices about cadence, depth, and area shift the balance between statistical power and systematic control, so field layouts are optimized across the sky from low extinction regions to calibration fields, weaving a pattern that supports precise measures of distances while leaving room for serendipity that often signals discovery. At the smallest resolvable scales, feedback from stars and black holes stirs turbulence that can mimic or mask subtle cosmological signals, so hydrodynamic simulations are anchored by observations of outflows, metallicity gradients, and hot gas fractions, ensuring that the bridge between astrophysics and cosmology carries the weight of inference without bending into confusion. The quiet confidence earned by this network of methods allows us to ask sharper questions about initial conditions, such as whether inflation left a specific spectrum of gravitational waves whose curl-like polarization would stand out against foreground dust, and if detected, those waves would measure an energy scale unreachable by colliders, connecting the first moments to the ever-widening now. Until that smoking gun appears, we work with what we have, which is already extraordinarily rich. A sky whose patterns of light and matter let us track a smooth evolution of the scale factor without invoking an outer wall, and as the catalogue of cross-checked measurements grows, the initial puzzle resolves into a narrative compass that points not outward to an edge, but inward to the rules that make edges unnecessary. In this flow, the next steps are natural rather than abrupt, because the same attention that stabilizes supernova brightness also clarifies standard siren distances. The same lensing maps that weigh dark matter halos also calibrate cluster masses used for growth, and the same radio intensity surveys that chart hydrogen at early times also give late-time rulers to measure geometry, each strand tightening the weave. As we approach the present boundary of knowledge, we do not pretend the story ends, but we respect how far it has carried us, to a place where the expansion rate as a function of time is not merely a slogan, but a curve etched by independent chisels, and the absence of an edge is no longer a riddle, but a corollary of a geometry that evolves according to what it contains. So we continue forward with the same rhythm, letting new instruments, better calibrations, and bolder cross-correlations refine the map of an edgeless universe. Because the surest way to honour the question that hooked us is to keep translating curiosity into measurement, linking the whisper of quantum seeds to the chorus of galaxies, all within a cosmos that grows everywhere without a shore. Having tied geometry to growth through multiple cross-checks, we can now follow the energy inventory across time by tracking how ordinary matter shifts from diffuse gas into stars while dark matter halos merge hierarchically, because the changing balance alters the thermal state of the intergalactic medium, modifies how galaxies bias the underlying field, and subtly feeds back on every distance probe that relies on accurate models of light propagation through a fog that brightens then thins. That thermal history is read through quasar absorption spectra, where the widths of hydrogen lines reveal the temperature of cosmic gas, allowing reconstructions of heating from ultraviolet backgrounds and from energetic outflows, which matters because hotter gas smooths small-scale features that would otherwise boost clustering, thereby influencing the translation from observed patterns to the true expansion curve. A complementary chronicle arrives from stellar archaeology in the halos of galaxies where ancient stars preserve chemical ratios set by the earliest supernovae. Those ratios tell us when the first heavy elements were forged, constraining how rapidly the earliest galaxies assembled within dark matter halos, which in turn fixes the timing of reionization that leaves geometric fingerprints on polarization and on the growth of structure. Moving seamlessly toward the cosmic microwave background without repeating earlier themes, we look to spectral distortions of that background, where small departures from a perfect blackbody, such as the mu-type and E-type distortions, would record energy released from decaying particles or from the damping of acoustic waves, turning the sky into a calorimeter that keeps the receipts for subtle processes otherwise invisible. Gravitational lensing of the background provides a second derivative view of structure by remapping small-scale temperature and polarization, and when these remappings are cross-correlated with galaxy surveys across redshift slices, the combined signal isolates the geometry that converts angles and redshifts to distances, strengthening constraints while cancelling nuisances that vary from map to map. A rare but telling observable is cosmic parallax, the expected drift of angular separations between far galaxies due to our motion and to long-term curvature effects, tiny in the extreme yet measurable with patient astrometry, and if detected it would give a direct geometric handle on spacetime without relying on standard candles, rulers, or dynamical assumptions. Standard sirens from gravitational waves add depth by offering an absolute scale free of brightness calibration. So as the network of detectors grows and baselines lengthen, we anticipate a catalogue that spans from the nearby universe to moderate redshift, enabling a joint fit where distances from waves meet redshifts from host galaxies to etch the expansion history with independent chisels. At higher energies, blazar gamma rays absorb on the extragalactic background light, and the energy-dependent attenuation traces the integrated star formation and dust reprocessing across time, so models that fit blazar spectra must also fit galaxy counts and infrared backgrounds, thereby tying the luminous history to the kinematics of the scale factor that set the stage on which these photons travelled. Closer to the present, we confront the subtle birefringence tests where the polarization plane of ancient light could rotate due to new physics, and any such rotation would not only hint at fields beyond the standard model but also complicate lensing reconstructions that assume a fixed baseline. Hence, precision cosmology now folds in cosmic birefringence as both a discovery channel and a calibration parameter. Strong lens systems continue to evolve from singular examples into populations, making it possible to stack time delay measurements, compare deflector kinematics across morphologies, and test whether mass profiles have evolved in a way consistent with the same expansion that we infer from background radiation, because the story is strongest when very different scales render the same verdict about distance. Voids give us another angle by acting as overgrown laboratories where relativistic light cone effects are amplified, so redshift space distortions, gravitational redshift, integrated potential changes become more measurable within their emptiness, furnishing fresh tests of gravity that do not rely on dense environments where messy astrophysics can overwhelm the signal. To keep the flow unbroken, we turn to the phase of baryon acoustic oscillations, a detail beyond the position of the ruler, because interactions with early relativistic species shift the phase slightly. Our precise measurements of that phase offer a census of light particle content that cross-checks inferences from the background radiation, again stitching particle physics to geometry. A parallel thread explores primordial magnetic fields that would twist polarization patterns, seed structure on small scales, and contribute to spectral distortions, making them detectable through a combination of microwave maps, radio surveys, and high-energy backgrounds. Thus, even cosmic magnetism becomes a tool for auditing how the early plasma bled its energy into the expanding stage. In the mid-redshift universe, neutral hydrogen mapping with 21 cm emission transforms cosmology into cartography, because with wide fields and coarse angular resolution, we can survey volumes that would take decades with galaxy spectroscopy, reading the imprint of acoustic oscillations and redshift space distortions in aggregate emission that follows the scaffolding carved by dark matter. Galaxy clusters remain sensitive thermometers and yardsticks, yet the modern approach is to combine X-ray temperatures, thermal Sunyaev-Zeldovich decrements, and weak lensing masses in a self-consistent loop, since none alone is free from complexities but together they triangulate the truth, yielding growth histories that must harmonize with the distance ladder and with background radiation. Another quiet probe is the distribution of satellite galaxies around massive hosts, where the count of low-mass companions tests the nature of dark matter and the efficiency of star formation at the faint end, while the anisotropy of their orbital planes can reveal dynamical histories, all of which must coexist with an expansion model that neither overclumps nor oversmooths the cosmos. Cosmic chronometers refine the direct mapping of the expansion rate by using spectral features in old stellar populations as clocks, and as calibration improves for stellar ages through better models of elemental abundances and stellar physics. These clocks promise a clean curve of the Hubble parameter versus redshift that sidesteps the brightest standard candles. Photometric surveys push to fainter limits where galaxy shapes are noisy and colours are uncertain, which is why end-to-end simulations that inject synthetic skies through real pipelines become indispensable, letting us measure shear biases, photometric redshift outliers, and selection effects in the same language that the data speak, ensuring that improvements in area and depth translate into honest cosmology. The kinematic Sunyaev-Zeldovich effect, already a tool for mapping flows, also enables measurements of the baryon fraction in large-scale structures by comparing momentum maps to gravitational lensing, which reveals how gas traces dark matter from filaments to clusters, tying the thermodynamics of the cosmic web to the same geometry that governs distance and time. Turning to topology with fresh eyes, one can search for statistical symmetry, breaking in the distribution of large voids and walls that might arise in compact spaces, a subtle signature distinct from matched circles. Thus, even in the absence of a direct wraparound, we can let the layout of emptiness and structure test whether our space is simply connected on scales beyond view. Beyond tests of the background, we examine the propagation of high-energy cosmic rays, whose arrival directions and energies are modulated by magnetic fields and photon backgrounds, offering a cross-check of the photon fields that also attenuate gamma rays, thereby linking energetic messengers to the star formation history that is itself sensitive to how quickly the universe dilutes. Spectral line intensity mapping extends past hydrogen to carbon monoxide and ionized carbon, capturing aggregate emission from dusty star-forming galaxies that would otherwise fall below detection. Because these lines sample different environments, they let us separate astrophysical evolution from geometry, tightening the isolation of the expansion history. As we consider possible cracks in the framework, we test energy injection scenarios from decaying or annihilating particles that would alter the ionization history, which would in turn shift the polarization peak structure of the background radiation and the thickness of the last scattering surface, yielding a lever arm that translates microphysical lifetimes into macroscopic signatures. The deepest lesson here is that distance in a living spacetime is not a mere ruler reading, but a synthesis of many clocks and rods, where clocks include radioactive dating in stars, pulsar timing in binary systems, and redshift drift, while rods include acoustic rulers, lensing distances, and standard siren amplitudes, all of which must agree within errors if the expansion law is correct. Our local group plays a special role by anchoring dynamics through precision measurements of proper motions for nearby galaxies, allowing a reconstruction of the gravitational field that binds our neighbourhood, and those reconstructions must be consistent with a global expansion that leaves bound systems intact, else a contradiction would appear at the very scales we understand best. Instruments poised for the near future bring sharper focus without breaking continuity, as wide-field infrared telescopes will harvest supernovae at redshifts, where dust is kinder. Giant ground-based mirrors will resolve lens substructure that perturbs time delays, and radio arrays will write three-dimensional maps of hydrogen that stretch from the end of reionization to relatively recent epochs. With each improvement comes a renewed emphasis on transparent methodology, including blind analyses where cosmological parameters remain hidden until pipelines are locked, open release of covariance matrices, a community challenges that pit algorithms against realistic mocks, because reliability in a universe without an edge is earned through procedures that others can replicate. If the equation of state of dark energy ever deviates even slightly from a constant value, it will appear as gentle curvature in the relationship between distance and redshift. Once independent growth measures are folded in, so the paired attack of geometry and clustering becomes more than belt and suspenders. It becomes the only honest route to telling whether the vacuum is truly constant. Modified gravity models that mimic a cosmological constant at the background level are pressed by lensing to velocity comparisons, which test the equality of the two gravitational potentials. Any slip between them would mark a departure from general relativity, hence the continuing push to measure both light deflection and galaxy motions across the same swathes of sky. Non-Gaussian initial conditions, besides their imprint on halo bias, also leave subtle signatures in the squeezed configurations of the three-point correlation, and because those shapes respond differently to late-time physics than to primordial processes, they let us separate the new from the ancient while keeping the flow toward our goal, a faithful map of the scale factor. At the longest wavelengths detectable, polarization curl patterns from primordial gravitational waves would set a scale for the earliest expansion, while careful cleaning of galactic dust and synchrotron emission protects that delicate signal, demonstrating again that understanding our own galaxy is part of measuring the whole, for the foreground is the first lens through which the universe speaks. Even if that signal remains elusive, the continued convergence among independent probes tightens the bounds on curvature, on the sum of neutrino masses, on the amplitude and tilt of the primordial spectrum, and on the time dependence of the vacuum-like component, turning what began as a question about edges into an inventory of the parameters that script the cosmic play. In the far future of our narrative, when the event horizon has closed over more distant structures, the records we compile today in microwave maps, lensing catalogues, and standard siren distances will stand as inscriptions that outlast the visibility of their sources, proof that an edgeless universe can be read with care even as its pages slip beyond view, leaving us with a truthful curve of distance against time. Carrying the thread forward from distance tests into the engines that light them, we examine how supermassive black holes co-evolve with their host galaxies through feedback that heats gas, launches outflows, and regulates star formation, since this regulation changes the supply of bright transients used as standard candles, while also sculpting the thermodynamic state of the intergalactic medium through which their light must travel. Because this coevolution unfolds within dark matter halos that merge hierarchically, we can read its timeline in the statistics of active galactic nuclei lifetimes, in the metallicity gradients of stars, and in the clustering of quasars across redshift, linking astrophysical histories to the same expanding geometry that turns redshift into distance, and distance into a record of how space-time stretches. The deepest radio timing experiments extend this narrative by listening for a stochastic background of gravitational waves from pairs of supermassive black holes, using pulsars as exquisitely stable clocks whose small schedule shifts reveal the gravitational murmurs of distant binaries, thereby transforming galactic archaeology into a chronometer for the assembly of structure across cosmic time. As these wave-based distances accumulate, they will join standard sirens from merging neutron stars to shape a purely gravitational distance ladder, one that sidesteps brightness calibration entirely, and when matched with spectroscopic redshifts of host galaxies, the result becomes a direct etching of the expansion history that can be compared against electromagnetic rulers and against lensing geometries. Meanwhile, the first generations of stars leave their mark through the damping wings seen in quasar spectra at the tail end of ionization, because neutral hydrogen in the intergalactic medium absorbs far ultraviolet light in a way that reveals the patchwork of ionized bubbles, letting us measure not only when the fog lifted but how quickly, which feeds back into models of star formation efficiency in young halos. This reionization timeline pairs naturally with the global 21 centimeter signal, a sky-wide dip or bump in radio brightness that arises when the spin temperature of hydrogen departs from the background radiation. Although that single global measurement is delicate, its shape and timing hold clues about the first sources of light and about how cosmic expansion cooled the gas between them. A detailed understanding of dust becomes necessary here because grains both obscure and re-radiate starlight, shifting energy from optical bands into the infrared, so models that connect galaxy colours to intrinsic luminosities must include dust grain physics tied to metallicity and star formation history, else our distance indicators drift and our volume reconstructions misread the geometry. To keep the flow unbroken, we move to cosmic magnetism, where large-scale magnetic fields thread galaxies and clusters, twisting polarization angles, guiding cosmic rays, and affecting the pressure balance of gas, with each of these effects showing up as small modifications to lensing reconstructions and to intensity maps that must be accounted for when drawing the curve of the scale factor. Energetic messengers then add another layer of checks, since high-energy photons from blazars are attenuated by the extragalactic background light in a way that depends on the integrated star formation history, which itself depends on how quickly the universe dilutes, tying gamma-ray spectra, galaxy counts, and infrared backgrounds into a single consistency test of expansion. In parallel, the kinematics of cold gas as traced by spectral lines such as carbon monoxide reveal how fuel flows within galaxies, informing models of feedback and star formation thresholds that determine the population of bright events used as cosmological beacons. Hence, a careful accounting of gas supply and turbulence becomes part of translating light into distance without bias. The cosmic esotropy principle continues to be tested by measuring the dipole pattern in the distribution of radio sources and in the flow of nearby galaxies, which must match the motion inferred from the background radiation, so any significant mismatch would hint at large-scale anomalies, while current results largely support isotropy within uncertainties that are shrinking as surveys expand. Topological questions never wholly retreat, therefore we search for subtle periodicities in the three-dimensional positions of rare objects that could signal a multiply-connected space. Yet even if such periodicity remains elusive, the very act of mapping deeper volumes with consistent selection gives tighter bounds on global shape, while keeping the edge-free nature of space intact. A natural continuation is the study of higher-order statistics like the 3-point and 4-point correlations of galaxy positions and of lensing shear, because these correlations carry information about nonlinear growth and bias that the 2-point function cannot capture, turning the cosmic web into a detailed ledger that reconciles astrophysics with the geometry of expansion. On the thermal side, the intracluster medium preserves memories of accretion and feedback in its pressure and entropy profiles, measured by X-ray observations and by the thermal scattering of background photons. And when these profiles are combined with weak lensing masses, we gain a clean growth history that can be set beside the distance-based history for a powerful mutual audit. Cosmic chronometers continue to refine the instantaneous expansion rate by using spectral features in old galaxies as clocks, and their sensitivity to stellar population modelling serves as a reminder that every rung of the cosmological inference ladder sits atop careful astrophysical foundations whose uncertainties must be propagated, not hidden, if the final curve is to be trusted. Continuity carries us to the realm of primordial fingerprints, where any tiny deviation from a perfectly Gaussian initial field would bias the abundance and clustering of the largest halos, allowing surveys of the most massive clusters to act as amplifiers for early universe physics, a lever arm that reaches from quantum seeds to present-day distances. Neutrino physics remains intertwined with structure, because the small but non-zero mass of neutrinos suppresses growth on scales below their free-streaming length, thus joint fits to lensing maps, galaxy clustering, and forest absorption spectra whittle down the allowed mass range, ensuring that the same expansion history that distances prefer is compatible with how matter actually clumps. The redshift drift experiment sits quietly at the horizon of feasibility, promising a direct measurement of the change in cosmic redshift over decades by watching narrow spectral lines slowly slide, which would provide a model-independent confirmation that the scale factor is accelerating now, a movie of expansion written frame by frame in the language of wavelength. Calibration remains the spine of the enterprise, so meticulous monitoring of instrument throughput, detector linearity, and atmospheric transmission turns the messy path from photons to numbers into a transparent pipeline, because only with such care can we claim that a tenth of a magnitude shift is physics, rather than a subtle drift in the machinery that gathers the sky. With an eye on the earliest times, spectral distortions of the background radiation offer a record of energy injection, from the damping of small-scale acoustic waves and from decays of unstable particles, meaning that even in the absence of a new map on the sky, we can gather new constraints by measuring how the spectrum veers by the smallest amount from a perfect blackbody. In the Middle Ages of cosmic history, neutral hydrogen mapping will turn the universe into a three-dimensional laboratory, where the acoustic imprint and the peculiar velocity signature can be tracked continuously across vast volumes, allowing a reconstruction of the expansion that is less vulnerable to the selection biases of individual galaxies, another route by which geometry is pinned. As the survey depth grows, selection functions, completeness corrections, and photometric redshift calibrations must be built into the likelihoods rather than patched afterward, because a small bias in the tail of a redshift distribution can distort the scale of the standard ruler, and the only antidote is to let the data-generating process inform the inference from the start. When these practices are adopted widely, joint analyses that weave distance indicators with growth probes and relic backgrounds become possible without double-counting information, yielding parameter constraints that are both tight and believable, while any residual tension becomes a signal worth chasing rather than an artifact of misaligned pipelines. Future instruments add sharpness without changing the melody, as giant optical telescopes will resolve lensing substructure that perturbs time delays, wide-field infrared observatories will find supernovae where dust is kinder, and radio arrays will map hydrogen from the end of reionization to later epochs, each facility enriching the same expanding tail with new angles. Alongside these advances, laboratory measurements of atomic transition probabilities, detector nonlinearity, and flux standards circulate back into cosmology, shrinking systematic flaws so that the remaining uncertainty truly reflects the sky, and not the apparatus, which is exactly what is required when the goal is to see gentle departures from a constant vacuum energy, if any exist. Returning to the structure that expansion leaves behind, voids provide geometric leverage through their nearly spherical shapes and low internal forces, enhancing the test that compares line of sight to transverse scales. while their interiors amplify relativistic light cone effects that offer new windows into the background dynamics. Galactic dynamics within the local group close the loop by showing how bound systems remain intact despite the global stretch, with proper motion measurements now pinning down orbits that test mass models and the gravitational field in our neighbourhood, verifying that the same theory that governs vast distances also predicts motions at humanly comprehensible scales. This steady accumulation of cross-checked evidence turns the original puzzle into a disciplined program where every step from photon counting to parameter inference is documented, reproduced, and examined by independent teams, so that what remains uncertain is named clearly, while what is established supports the view that space grows by an internal rule, rather than by pushing against an absent wall. In that spirit, we press onward to the frontier where deviations could lurk, scrutinizing polarization patterns for parity violation, seeking small rotations that would reveal cosmic birefringence, tracking any anomaly in the largest angular modes with sober statistics, and designing experiments that can either confirm such hints or retire them, thereby letting the edgeless model earn its keep. The enduring conclusion, approached not by repetition but by accumulation, is that geometry, growth, and relic light tell one coherent story when they are permitted to speak together, a story in which horizons limit knowledge without imposing an edge, in which distances evolve according to energy and pressure, in which the cosmos remains borderless even as it enlarges with time. Building on the coherence earned so far, we move into clocks and rulers that have only recently matured, beginning with fast radio bursts whose dispersion measures tally free electrons along the line of sight so that, once a host galaxy redshift is secured, each burst links the ionized content of the intergalactic medium to cosmic distance, turning short radio flashes into probes of how space has thinned as the scale factor rose. Those flashes do double duty by helping solve the missing baryon problem, because the integrated electron columns inferred from many sightlines add up to the expected allotment of ordinary matter outside galaxies, and that census anchors models of gas heating and feedback, which otherwise blur the translation from observed structure into the distance scale that an expanding spacetime demands. A complementary ruler emerges from surface brightness fluctuations in the unresolved glow of old stellar populations, where pixel-to-pixel variations fade with distance in a way that is insensitive to dust at optical wavelengths, so when calibrated with nearby galaxies, the method extends the ladder into regimes that overlap strongly lensed systems and time delay distances for mutual checks. Distance duality, the theorem equating luminosity distance with angular diameter distance times 1 plus redshift squared, becomes a target rather than an assumption when we test it by pairing thermal Sunyaev-Zeldovich measurements of cluster sizes with X-ray brightness profiles, because any opacity or exotic photon physics would tilt that balance and thereby flag a hidden bias in expansion inferences. Another set of rulers comes from strong lensing of supernovae, where the brightness evolution of a multiply-imaged explosion provides accurate time delays without the chaotic flicker of quasars, enabling geometric distances with cleaner light curves that fold neatly into the web of expansion probes already in hand. The sky also offers a quiet geometric audit through Etherington-style consistency tests that compare galaxy number counts, shapes, and magnifications across foreground and background slices, because the same metric that stretches wavelengths must also set the amplitude of lensing distortions, so agreement across these channels becomes a direct verdict on the way space-time expands. On the blueprint of recombination, we can push beyond earlier summaries by noting that two photon decays of hydrogen's metastable states and helium's cascade lines subtly sculpt the width of the last scattering surface, which in turn adjusts the damping tail of the temperature spectrum and the polarization bump, making atomic physics an indispensable cog in the machinery that maps early light to present distances. White dwarf cooling sequences and the ages of the oldest globular clusters add a chronometric cross-check on the integrated expansion history, since the thermal clocks of slowly fading stellar remnants set a hard lower limit on the age of the cosmos, and that limit must match the integral of the Hubble parameter over redshift when the matter and vacuum energies are correctly weighed. The pattern of baryon acoustic oscillations carries not only a position, but separate radial and transverse components, so surveys that measure both resolve the Hubble parameter as a function of redshift and the angular diameter distance independently, a split that empowers detailed reconstructions of the scale factor without leaning on any single standard candle. Next, we refine lensing by isolating the elusive curl free and divergence-free modes of cosmic shear, because any residual curl beyond that expected from systematics would signal an unmodelled contaminant or new physics, and bringing those modes under control transforms shear maps from elegant pictures into precision rulers that are safe to combine with other probes. Gravitational wave catalogues then expand into the regime of black hole neutron star mergers and eventually black hole mergers with statistical host identification, where even without a bright counterpart, a probabilistic association with galaxy maps yields a distance redshift relation, stacking many events until the curve of expansion sharpens under purely gravitational scrutiny. High-energy transparency offers an orthogonal test as very high-energy gamma rays from distant blazars traverse photon seas that should attenuate them, so any anomalous survival could point to photon mixing with axion-like particles in magnetic fields, a mechanism that would mimic reduced opacity and bias distances, unless constrained jointly with infrared background and lensing measurements. Cosmic opacity in a more mundane guise is audited by comparing supernova luminosity distances to baryon, acoustic oscillation angular diameters through the distance duality relation, with dust models and scattering physics folded into the likelihood so that any residual mismatch becomes a genuine whisper about photons rather than a misread of the sky. Radio intensity mapping of neutral hydrogen adds velocity information through redshift space distortions, letting us extract the growth rate in the same volumes that yield geometric rulers, and the joint fit pins geometry and growth in a single breath, so that modified gravity models cannot hide in the gap between them. At still higher resolution, microlensing of quasar images by stars in a lensing galaxy introduces chromatic magnification that can be modelled and removed, revealing time delays with reduced scatter and enabling cleaner distances, while the microlensing itself becomes a laboratory for accretion disk sizes that inform the astrophysics feeding our brightest lighthouses. Pulsar timing arrays continue to detect the nanohertz gravitational wave background, consistent with a population of inspiraling supermassive black hole binaries, and the evolving amplitude and spectral shape of that background connects galaxy merger rates to the history of massive halo assembly, an arc that must align with the same expansion timeline we derive from electromagnetic rulers. The isotropy of cosmic acceleration is being checked directly by mapping the Hubble parameter across the sky, with hemisphere splits of supernova samples, and by comparing dipoles in radio source counts to the motion inferred from microwave background dipole measurements, ensuring that any hint of a large-scale anisotropy is either confirmed with multiple traces or dismissed as selection bias. In the intergalactic medium, the thermal history after reionization imprints a temperature-density relation that affects the small-scale shape of the Lyman alpha forest power spectrum, so precision measurements of that spectrum calibrate feedback and heating while backing out the underlying matter, clustering that serves as a growth cross-check against geometry. Subtle relativistic effects in galaxy number counts, including Doppler terms, gravitational redshift, and lensing magnification, enter at large scales with characteristic angular dependencies, and modelling them turns wide-area surveys into laboratories for general relativity on cosmological distances, complementing the purely geometric tests with dynamical consistency. The cosmic infrared background fluctuations, sourced by the cumulative light of faint galaxies, trace star formation in environments beyond individual detection, and cross-correlation of those fluctuations with lensing maps teases out the bias between light and mass, keeping the translation between brightness and distance grounded in how structure actually forms. Moving to the nearby universe, we use precise geometric distances from water megamassa disks orbiting black holes in a handful of galaxies, where Keplerian rotation and proper motion deliver purely dynamical yardsticks that lock the zero point of other indicators and reduce the room for calibration drift along the ladder. Within the Milky Way, the parallax revolution from space-based astrometry refines the distances to variable stars that serve as rungs, while independent anchors from mirror variables and eclipsing binaries diversify the portfolio, a redundancy that immunizes the ladder against any single population's quirks. Theoretical priors are also being stress-tested through non-parametric reconstructions of the expansion history, where Gaussian process techniques and spline models let the data sketch the curve of the Hubble parameter without assuming a specific dark energy form, and the resulting model independence clarifies which features are truly measured. At the frontier of topology, searches for ghost images of rare objects at different redshifts and angles push the limits on multiply connected spaces far beyond the horizon scale. So while no repetition patterns have convinced the community, the negative result itself tightens how confidently we can say that edgelessness does not require a short wraparound. Cosmic birefringence remains under watch as polarization maps sharpen, for a rotation of the polarization plane across the sky could hint at new scalar fields coupled to photons, and that same rotation would subtly bias lensing reconstructions unless included, so each progressive map is both a science target and its own calibration manual. Intracluster gas physics matures through joint fits to X-ray spectra, thermal and kinematic Sunyaev-Zeldovich signals, and weak lensing masses, converting turbulent plasmas into honest mass proxies, which in turn yield an abundance evolution that must match the pattern of distances if the same expansion law governs both geometry and growth. A final arc in this segment returns to fast radio bursts with host dispersion, rotation measures, and scattering tails that reveal magnetic fields, turbulence, and electron densities along paths that thread filaments and voids, letting radio burst map the scaffolding of matter that expansion has stretched while offering yet another independent tally of how distances scale with time. Taken together, these additions do not reset the story but extend it naturally, stringing new instruments and ideas onto the same spine where geometry, growth and relic light agree, so that the borderless expansion continues to be not a metaphor but a measurable unfolding, traced by clocks that tick in radio and light and gravity as the universe enlarges without a shore. Flowing naturally from radio flashes that weigh the web, we turn to the metals woven into intergalactic space, because damped hydrogen, absorbers and metal line systems in quasar spectra chart how galaxies enriched their surroundings while the universe expanded, and by comparing the evolving abundances of elements like carbon, oxygen, silicon and iron against the redshift of each system, we obtain a chemical timeline that must harmonize with the star formation history inferred from galaxy light, thereby connecting the growth of heavy elements to the same metric that stretches distances and cools the cosmic gas. Tomographic maps assembled from many close sightlines toward background galaxies now reconstruct three-dimensional slices of the cosmic web, letting us watch filaments feed halos whose star formation rates respond to their environment, and when these maps are cross-correlated with weak lensing convergence fields, they reveal how baryons trace dark matter across scales, a necessary calibration for any probe that converts a pattern on the sky into a statement about the evolving scale factor. The kinematics of galaxies contribute a complementary yardstick through relations linking internal motion to luminosity, where rotating disks obey Tully-Fisher-like ties and pressure-supported spheroids follow Faber-Jackson-like trends, so once carefully calibrated for population age and dust, these relations extend distance estimates into regimes that overlap with strong lensing distances and baryon acoustic rulers, stitching astrophysics to geometry without breaking the flow of evidence. In strongly lensed systems, we press deeper into the mass sheet degeneracy that can bias time-delay distances, breaking it with stellar velocity dispersions of the deflector, with lens environment mapping, and with high-resolution imaging that constrains the angular structure of the mass, because only by taming these lensing subtleties do time delays yield expansion measurements that are as clean as their elegant geometry promises. Turning back to the background glow with fresh eyes, delensing techniques now peel away the gravitational distortions from polarization maps to expose the faint curl pattern that inflation would seed, and the success of delensing depends on accurate mass maps from galaxy surveys and cosmic microwave background lensing, an interdependence that exemplifies how growth and geometry must sing together if we are to read a pristine early universe signal. The neutrality of hydrogen at cosmic dawn can also be charted statistically through the distribution of Lyman alpha emitters, whose visibility depends on the ionized fraction of their neighborhoods, so the evolving fraction of bright emitters across redshift traces the clearing fog of reionization, and when combined with 21 centimeter intensity maps, the two signals compose a duet that times the first lights against the expanding background. Closer to the thermal heart of structure, intracluster gas profiles encode assembly histories in their temperature and entropy gradients. And when these profiles are matched to weak lensing masses, the resulting cluster abundance as a function of redshift gives a growth curve that must agree with geometric distances, else either our gas physics is incomplete or our understanding of cosmic acceleration needs revision, a fork that forces rigor on both sides. Big Bang nucleosynthesis cements the early narrative with a sharp chronometer in the deuterium abundance measured in pristine gas clouds, because deuterium is burned away in stars and survives only in regions unprocessed by generations of fusion. So its observed fraction singles out the cosmic baryon density, and that density must align with the value inferred from the background radiation and from the dispersion measures of fast radio bursts, a three-way agreement that leaves little wiggle room. The homogeneity scale of the universe can be tested directly by counting galaxies in progressively larger volumes and measuring the fractal dimension that approaches 3, a check that confirms the statistical uniformity assumed by the equations we use, and any departure on very large scales would echo through every distance relation, which is why wide-area surveys are designed to push the homogeneity test to horizons that rival the depth of our other probes. Gravitational waves deliver yet another handle on the laws guiding expansion by comparing their propagation with light, since the near-simultaneous arrival of waves and photons from a neutron star merger demands that their speeds match to exquisite precision, thereby ruling out broad classes of modified gravity that would alter the friction or speed of gravitational waves, and tightening the circle around a cosmology driven by a nearly constant vacuum energy. High-energy transparency continues to press on exotic physics, as gamma rays from distant blazars traverse the infrared background of all starlight ever emitted, because any unexpected survival of the highest energy photons would hint at photon mixing with ultralight bosons in cosmic magnetic fields, which would mimic a lower opacity and skew distance inferences, so joint fits with lensing and infrared measurements guard the expansion history from such misdirection. The cosmic infrared background itself, when decomposed into fluctuations, traces star formation in galaxies too faint to resolve individually, and cross-correlation with lensing maps reveals how that hidden light populates dark matter halos, turning the hazy glow into a census that informs both the energetic history of the universe and the bias parameters needed to translate clustering into geometry. Non-parametric reconstructions of the Hubble parameter as a function of redshift, using Gaussian processes or flexible splines, let the data sketch the expansion curve without allegiance to a particular dark energy model. And this agnostic sketch can then be compared against predictions from a cosmological constant or from gently rolling fields, elevating the role of the sky over that of assumption in deciding how the scale factor is evolved. Counts of the most massive halos at high redshift act as amplifiers for the initial conditions because their abundance is exponentially sensitive to the amplitude and non-Gaussian nature of primordial fluctuations, so cluster surveys that reach early times can test inflationary predictions even as they map the growth that must remain consistent with distance measures, binding the first instance to the present expansion with a quantitative thread. The Lyman alpha forest power spectrum, shaped by the interplay between gas temperature and gravitational collapse, nails down the small-scale matter, clustering that neutrinos damp through their free streaming, so by marrying forest measurements to lensing and galaxy surveys, we whittle away uncertainty in the sum of neutrino masses, closing a loop where particle properties and cosmic geometry constrain one another. At the grandest angular scales, relativistic corrections to galaxy number counts imprint distinctive signatures that depend on gravitational potentials, Doppler effects, a lensing magnification, and modelling these contributions turns wide-area maps into laboratories for general relativity on cosmic distances, a dynamical complement to purely geometric tests that together patrol the frontier where departures might hide. Etherington-style consistency can be sharpened further by comparing supernova luminosity distances with cluster angular diameters and with magnification derived from shear, because in a transparent metric theory these three views must align, and any tilt among them would point to photon absorption, axion-like conversions or calibration drift, exactly the sort of pitfalls that precision cosmology must expose rather than absorb. The cosmic chronometer method matures as stellar population models improve with better atomic data and a firmer grip on elemental abundance patterns, turning age differences between passively evolving galaxies into a direct measure of the expansion rate. And because this route skips standard candles and rulers, it offers an independent sketch of the same curve that supernova, baryon acoustic oscillations, and lensing have drawn from their own angles. In the nearby universe, water megamaser disks orbiting supermassive black holes yield geometric distances from pure dynamics by combining proper motion, orbital speeds, and angular sizes, an anchor that sets the 0 point for other methods and insulates the ladder from compounding uncertainties, a reminder that local precision is the foundation on which distant inference rests. Astrometry from space keeps sharpening the parallax map to variable stars that seed the first rungs, while eclipsing binaries and mirror variables supply independent calibrations that reduce population-specific quirks, and as these anchors settle the lower tiers, the higher tiers of supernovae and surface brightness fluctuations can be trusted to carry us cleanly into the realm where geometry is read from the faintest light. Beyond photons, pulsar timing arrays continue to refine their detection of a nanohertz background consistent with an ensemble of supermassive black hole binaries, and the amplitude and spectral slope of that background knit together galaxy merger statistics with halo growth in a way that must track the same expansion history, mapped by electromagnetic rulers, closing another loop on consistency. At the interface of theory and observation, multi-tracer strategies beat cosmic variance by comparing differently biased populations inhabiting the same volume, letting the largest scale modes be measured more cleanly than any single tracer could manage. Those modes in turn lock down the geometry on scales where the question of homogeneity is most acute. Finally, we circle back to the guiding question without retracing steps by noticing how every one of these clocks and rulers ultimately ties to the simple fact that a metric evolves with the contents of the cosmos, so that the absence of an edge becomes not a poetic flourish but a measured property of a space-time whose distances change with time, knitted together by metals in the web, echoes in the background light, waves in gravity, and the quiet geometry that lets them agree. From the chemical history etched into the intergalactic medium, we flow to the direct imprint of time itself on light curves, because in an expanding space-time, photons not only stretch in wavelength, but events unfold more slowly when viewed at high redshift. So the rise and fade of distant supernovae exhibit cosmic time dilation by the factor of 1 plus redshift, a clean kinematic signature that requires no model of dust or evolution, and that complements distance-based inferences with a clock written into the sky. That same temporal stretching appears in active galactic nucleus variability and in gamma-ray burst afterglows once selection effects are treated with honesty, which matters because multiple independent clocks strengthen the case that it is space itself that evolves rather than tired light or hidden scattering, binding our narrative of an edgeless expansion to measurable delays that any careful telescope can verify across many wavelengths. Where clocks begin to merge with rulers, we meet standardizable explosions beyond the familiar supernovae, such as gravitationally lensed supernovae whose multiple images stagger in time, thereby providing both a time delay distance and a dilation check in one astrophysical package, a dual role that encourages surveys to seek these rare alignments, with cadence tuned for both geometry and timing. On the largest canvases, the Rees-Siyama effect adds a late-time echo to the integrated Sachs-Wolf signature by allowing evolving gravitational potentials to tweak photon energies as structures grow non-linearly, a whisper that confirms both the presence of accelerating expansion and the reality of structure growth, knitting dynamical change to geometric evolution without breaking the smooth flow of evidence. Deep radio maps then let us weigh pairwise motions through the kinetic Sunyaev-Zeldovich effect, where hot plasma in galaxy clusters imparts tiny Doppler shifts to background photons that reveal bulk flows on scales of tens of megaparsecs, and those flows must trace the same growth history that lensing and redshift space distortions demand if our picture of a metric-driven expansion is to remain coherent. Shifting scale again, we consider gravitational redshift within clusters, a minuscule but measurable shift in spectral lines from galaxies deep in potential wells relative to those closer to the outskirts, a purely relativistic height effect that validates the mapping from light to gravitational potential and secures the bridge between local wells of gravity and the global expansion they inhabit. Turning to the earliest galaxies brought into view by powerful infrared observatories, we fold their surprising brightness and compactness at very high redshift into models that respect both the timing of reionization and the supply of baryons, ensuring that the abundance of luminous candidates aligns with a growth narrative governed by the same scale factor history traced by acoustic rulers and relic radiation. As counts of faint galaxies rise, we confront lensing magnification bias head-on, because foreground structure not only shears shapes, but changes apparent number densities by brightening some sources into a survey while dimming others below thresholds, and modelling this effect turns what could be a nuisance into a tool that cross-checks mass maps against galaxy catalogues across redshift slices. The cosmic web's emptiest rooms provide another geometric lever, since the near-spherical expansion of voids enhances the Alcock-Paczynski comparison of tangential and radial scales, while their low densities suppress messy astrophysical complications. So stacking many voids across redshift transforms absence into a standardizable shape that listens closely to the background cosmology. In parallel, we refine our reading of a weak lensing by separating E-mode shear from spurious B-mode patterns arising from residual systematics or intrinsic alignments, because only when the B-modes are tamed do shear maps become clean rulers, and the remaining E-mode signal then dovetails with galaxy clustering to tie growth and geometry in a way that modified gravity cannot easily evade. Having learned to Dellen's polarization to seek primordial curls, we apply the same discipline to galaxy surveys by forward modelling the full path from dark matter to stars to light, letting hydrodynamic simulations inform bias parameters so that the translation from maps of brightness to maps of mass respects feedback, metallicity, and gas thermodynamics without smuggling in hidden assumptions. At intermediate redshifts, the angular correlation of Lyman alpha emitters reveals the topology of ionized bubbles, which, when cross-correlated with 21 cm intensity maps, yields a movie of how the intergalactic medium cleared, and that movie's cadence must match the star formation history inferred from ultraviolet luminosity functions if the expanding background is being read correctly. Standard sirens advance from isolated events to a networked chronicle as detector sensitivity grows, bringing black hole neutron star mergers with occasional electromagnetic counterparts that pinhost redshifts, while dark sirens without counterparts are localized statistically against wide galaxy catalogues, so the purely gravitational distance curve gains both precision and reach. From the standpoint of topology, we push for matched polarization angle patterns on the sky rather than only temperature circles, since polarization carries independent information about the geometry of last scattering, and any repeating motif would become a smoking signal of global connectivity on scales rivaling the horizon, a test that remains elegant even if it returns a null. The cosmic infrared background steps beyond a mere census when cross-correlated with weak lensing convergence, because such correlations expose how dust-rich star formation populates halos across mass and time, reducing the uncertainty in how light traces mass, and tightening the conversion from clustering amplitude to statements about the expansion history. Precision does not live in instruments alone, therefore blind analyses where cosmological parameters stay hidden until pipelines are final ensure that choices are not tuned by subconscious desire, and when the blinds are lifted, the agreement or tension among supernovae, acoustic rulers, lensing, and sirens carries the weight of an honest conversation with the sky rather than a negotiation. At the particle frontier, we note that ultralight axion-like fields would imprint a small-scale cutoff in the matter-power spectrum, while potentially inducing cosmic birefringence. So the combination of Lyman alpha forest small-scale clustering with polarization rotation searches becomes a cross-discipline sieve that either traps such fields or tightens the mesh through which theory must pass. Galaxy kinematics offer compact yardsticks through the Tully, Fisher and Faber-Jackson relations only if population effects are controlled. Hence, infrared observations that minimize dust and age biases are paired with accurate rotation curves and dispersion profiles, transforming nearby dynamical regularities into distance estimates that overlap lenses and acoustic rulers for redundancy. The intergalactic medium after reionization retains a thermal memory that slowly cools with expansion while being reheated by structure formation, and this temperature-density relation sculpts the fine shape of the Lyman alpha forest power spectrum, letting careful fits extract the underlying matter, clustering with enough reliability to press neutrino mass constraints that harmonize with lensing. A subtle but telling geometric test comes from distance duality, which says that in a transparent metric universe, the luminosity distance and angular diameter distance are linked by a specific factor. So by pairing supernova brightness with cluster sizes from Sunyaev-Zeldovich plus X-ray profiles, we verify that photons have not been lost to exotic conversions, protecting expansion inferences from hidden opacity. Where structure thickens into clusters, the combination of weak lensing masses with thermal and kinematic Sunyaev-Zeldovich signals turns the intracluster medium into a calibrated mass proxy, and the abundance of such calibrated clusters as a function of redshift becomes a growth history that must sing in tune with the distance-based score if dark energy is truly simple. Fast radio bursts return bearing rotation measures that trace magnetic fields along filaments and through cluster outskirts, complementing dispersion measures that count electrons. So together these radio flashes sketch both the amount of gas and the strength of cosmic magnetism, adding physical texture to the scaffolding whose geometry we read with acoustic rulers and lensing. In the nearby volume, precise geometric distances from water megamaser disks orbiting supermassive black holes continue to anchor the ladder, their Keplerian motion and angular sizes turning dynamics into meters and parsecs without recourse to population assumptions, a foundational certainty that propagates upward through every standard candle and ruler we trust at greater distances. Astrometry strengthens those foundations as space-based measurements refine parallaxes to variable stars, while eclipsing binaries and mirror variables deliver independent calibrations, and this diversity of anchors immunizes the entire enterprise against quirks in any single stellar population, a practical necessity when sub-percent precision in expansion is the target. Finally, the flow of evidence returns to its quiet center, where geometry, growth, clocks, and rulers converge, because the absence of any edge is no longer a philosophical flourish, but a measured property of a space-time whose distances change predictably with energy and pressure, a stage on which galaxies evolve, clusters breathe, voids expand, photons cool, waves ring, and every independent probe, from radio flashes to polarization curls, keeps reciting the same long sentence about a universe that grows everywhere at once. As we tilt toward a conclusion, the picture that has unfolded remains exquisitely empirical, with each observation a stitch that binds a fabric whose curvature evolves according to what it contains. So the edgeless growth of space is not an ornament, but a measured rule that turns redshift into time, lensing into mass, and relic glow into a ledger of beginnings that still illuminates the distances we read today. You can see the discipline of this story in how independent clocks and rulers converge on the same arc, where standard candles, acoustic peaks, weak shear, fast radio burst dispersion, and gravitational-wave sirens cross-check one another until the remaining disagreements are small enough to name, characterize, and resolve through better calibration rather than through hope. What once sounded like a paradox about edges now dissolves into geometry, because a metric that grows requires no wall to push against, only energy density and pressure to guide its pace, with dark matter shaping the knots of structure and dark energy setting the late-time tempo that gently accelerates the cosmic expansion. With that geometry in hand, we can forecast responsibly without theatrics, projecting that distant galaxies will fade beyond a future event horizon, while our local group remains gravitationally bound, leaving a long era where stars dim, gas thins, and background light redshifts ever further as the scale factor keeps climbing. Black holes will dominate the late inventory of compact objects, then evaporate over stupendous times through Hawking radiation, dribbling energy back into a space that continues to expand, a slow exchange that honors general relativity locally while respecting the global trend set by the energy content. Thermodynamics shadows this future because horizons carry entropy and temperature, suggesting that acceleration writes an arrow of time, not only in cooling matter, but in the flow of information, a perspective reinforced by the way structures stop growing once vacuum energy rules, even as bound islands continue their quieter evolution. If protons decay, the last traces of ordinary matter will drift into light and leptons across epochs that dwarf stellar lifetimes, while if they do not, degenerate remnants, and black dwarfs will persist much longer, either way inside a space-time whose distances keep changing in the same edgeless manner we measure today. The enduring lesson for the near term is methodological, because every percent of precision we gain comes not from clever phrasing, but from deeper intercomparisons, where the same sky is interrogated in photons, neutrals, and gravitational waves until only robust features remain, immune to the quirks of a single technique. This is why the next decade places equal weight on instruments and on honesty, leaning into blind analyses, repeatability across pipelines, synthetic skies that pass through real software, and open data releases that invite independent attempts to reproduce the curve of expansion from end to end. When tensions appear, they become opportunities rather than crises, because a small mismatch between early universe inferences and late-time ladders can be a lantern that finds a calibration slip, a population bias, or a gentle new degree of freedom. each possibility tested by cross-correlated maps that favour truth over convenience. Even the persistent unknowns are narrowed by this lattice of tests, as neutrino masses are hemmed in by small-scale clustering, cosmic birefringence is cornered by polarization patterns, and exotic opacity is fenced by distance duality, leaving fewer refugees where misunderstanding can masquerade as discovery. Against this disciplined backdrop, the original question reads differently, because asking why space expands without an edge is to ask how general relativity responds to content, how curvature follows energy, and how a nearly uniform bath at the beginning evolves into a structured cosmos without invoking any outside. Inflation remains the leading prelude to that beginning because it explains the flatness, the near-scale invariance, and the horizon-wide coordination of the microwave background, while still inviting sharper tests through polarization curls and spectral distortions that could take the measure of its energy scale. Dark energy stays simple in the data so far, acting like a near-constant vacuum density. Yet the program refuses complacency, pairing geometry with growth to check for even a slight drift in its equation of state, or for a slip in gravitational potentials that would hint at modified gravity on the larger scales. Dark matter remains gravitationally cold and quiet in its interactions with light, but small halos, strong lensing substructure, and the Lyman alpha forest keep testing whether it is perfectly cold or only cool, whether it self-interacts or whether wave-like behavior rounds its smallest clumps, each scenario facing data across redshift. The intergalactic medium continues to be our honest mirror because it reacts to galaxy feedback, ultraviolet backgrounds, and the slow cooling from expansion, recording those influences in absorption lines whose widths and clustering give us a thermometer, a barometer, and a clock all at once for gas between the galaxies. Ionization's timeline is now pinned from multiple sides, with Lyman alpha emitters, quasar damping wings, and 21 centimeter statistics teaching us when the fog lifted and how patchy that dawn was, a history that must agree with the abundance of early galaxies whose light first carved clearings in the neutral gas. Standard sirens grow from novelty to norm as detectors lengthen their baselines and sharpen localizations, bringing a gravitationally calibrated distance scale that ignores dust, stellar evolution, and flux standards, while partnerships with wide galaxy catalogues supply the redshifts that etch the curve in purely gravitational ink. Fast radio bursts keep the electron sensors honest by adding lines of sight far beyond the reach of pulsars, so dispersion measures join lensing and clustering to reveal both how many free electrons float between galaxies and how they are arranged within filaments and halos that ride the expansion. Clusters remain the thermal keystones of growth, where X-ray temperatures, Sunyaev-Zeldovich decrements, and weak lensing masses together produce a mass-calibrated census across redshift, a record that must harmonize with the distance-based history or else ask for revisions in feedback, gas physics, or gravity itself. Voids, the spacious counterpoints to clusters, turn absence into geometry by enhancing the Alcock-Beksinski test, with clean shapes and low internal forces, making emptiness a ruler whose tick marks are large, legible, and relatively free of astrophysical clutter. Time dilation in distant transients closes the loop on kinematics, because when supernova-like curves stretch exactly by 1 plus redshift, the sky itself whispers that this is not tired light, but a living space-time whose intervals grow along with its lengths. Where philosophy once asked for an edge, physics now supplies horizons that respect causality rather than borders, so the observable sphere is a light-built limit that expands as time passes, while the global topology can still be finite or infinite with no contradiction to the measurements in hand. In the very far future, the record we write today in microwave maps, lensing catalogues, siren distances, and dispersion measures becomes a time capsule for observers who may see little beyond their local group, proof that an edgeless universe can still be read by the fossils of its own light. The practical consequence now is focus, because the most fruitful labour is to lower systematic flaws until the remaining uncertainties belong to the cosmos, rather than to the camera, an ethos that has already turned a poetic question into a quantitative account of how distance itself evolves. So we finish not with a flourish, but with a clear sentence written across the sky, that space expands everywhere at once without needing an outside, that its pace is governed by energy and pressure, that its story is told by light, gas, galaxies and waves, and that the absence of an edge is not an absence of explanation, but the explanation, a geometry that grows because of what it holds. Leaning into the final synthesis, we link the whole chain from first light through late acceleration by tracing how the same metric that lengthens wavelengths also sets the angular ruler for baryon acoustic peaks, while weak shear weighs the scaffolding those peaks foretold, and the standard sirens carve a parallel distance scale immune to dust, so that geometry, growth, and clocks interlock into one narrative whose edgeless stage is not assumed but measured with instruments that talk to one another across the spectrum. The coherence of that narrative sharpens when dispersion measures of fast radio bursts tally electrons in filaments that lensing has already mapped, and when the same sightlines reveal rotation measures that sketch magnetic fields draped over cluster outskirts, because those fields guide cosmic rays whose gamma signatures test the extragalactic background light that blazes traverse, closing a loop where radio timing, lensing patterns, and high-energy transparency all answer to the same expanding geometry. Cosmic time dilation then serves as the kinematic refrain that runs beneath the melody, with supernova light curves stretched exactly by 1 plus redshift and quasar variability, echoing the same factor once selection is cleaned, a clockwork that needs no model of dust or evolution to declare that intervals themselves grow as the scale factor grows, which is what an edgeless metric does when it follows the stress energy written into the sky. Clusters and voids continue to speak in complementary dialects as mass-calibrated abundance across redshift charts, the slowing of growth under vacuum dominance, while stacked void shapes amplify the Alcock-Paksinski comparison of radial to tangential scales. So the densest knots and the broadest hollows together verify that distances and dynamics obey the same late-time acceleration predicted by a nearly constant dark energy. Delensing now polishes polarization maps, so the faint curl pattern that inflation might have imprinted can stand clear of intervening structures, with success hinging on accurate mass maps from galaxy surveys and cosmic microwave background lensing, which means a detection would tie quantum fluctuations at the beginning to the same gravitational scaffolding that shapes present-day shear, a single arc from first instance to current geometry. Spectral distortions of the residual glow supply a quiet ledger for energy injections that standard images cannot see, because even tiny departures from a perfect blackbody betray acoustic damping or particle decay in the young plasma, letting us test early heating while cross-checking nucleosynthesis, baryon density and microwave background inferences that already anchor the expansion curve. In the nearby universe, pure dynamics keep the ladder honest, as water megamassa disks orbiting black holes deliver geometric distances from proper motion and rotation, while space-based astrometry refines parallaxes to variable stars that seed the first rungs. So every high redshift statement about the Hubble parameter still rests on orbits and angles we can watch move across the detector. Radiocartography of neutral hydrogen turns cosmology into mapping by reading the acoustic imprint and the redshift space distortions in aggregate 21 centimeter emission across volumes that dwarf classical redshift surveys, which lets the same instrument recover geometry and growth in one sweep, squeezing modified gravity models that might match distances while failing the velocity field. Higher order statistics deepen the audit as 3-point and 4-point correlations in galaxy positions, and shear fields teach us about nonlinearity, bias, and any primordial non-Gaussianity. So the Webb's triangles and quadrilaterals become forensic tools that must agree with the 2-point rulers, or else flag either hidden systematics or a real crack where new physics could enter. The intergalactic medium remains a responsive barometer because its temperature-density relation after rionization sculpts the Lyman alpha forest power spectrum on small scales, and that spectrum, when married to lensing and galaxy clustering, weighs neutrino masses whose free streaming suppresses growth just enough to be seen, tying particle properties to the very curve of distance with which we began. Strong lensing distances grow cleaner as mass sheet degeneracy is broken by stellar kinematics and environment mapping, while supernovae caught in multiply imaged arcs add time delays with tidy light curves, so geometric distances from bent light now stand alongside acoustic rulers, sirens and chronometers without leaning on any single calibration, a redundancy that is the signature of maturity. Pulsar timing arrays keep listening to the nanohertz hum of supermassive black hole binaries, turning galaxy merger histories into a gravitational wave background whose amplitude and slope must match the same halo growth inferred from clustering and lensing, an elegant cross-check that welds the dynamical past of galaxies to the expansion history read from light. Opacity audits protect geometry by comparing supernova luminosity distances with cluster angular diameters inferred from Sunyaev-Zeldovich plus X-ray profiles under the distance duality theorem, while gamma transparency of blazars across the infrared photon seaguards against exotic photon mixing that could counterfeit dimming, together securing the photon channel through which we read the metric. Topology remains watchful in the background as searches for ghost images or matched polarization motifs keep tightening the leash on multiply connected spaces, yet the edgelessness we measure does not depend on a short wraparound, only on the local rule that distances between comoving points grow with the scale factor, a rule we have seen written in rulers, clocks, and waves. Looking forward responsibly, we expect catalogues of standard sirens, lensed supernovae, hydrogen intensity maps, and deep weak lensing to render sub-percent constraints on curvature, neutrino mass sums, and any drift from a constant vacuum equation of state, so that if new physics lurks, it will reveal itself not by rhetorical surprise, but by a pattern of small, stubborn departures across many independent probes. What matters most as we close is not a flourish, but a method. The habit of triangulating distance with many instruments that fail differently, of publishing pipelines and covariance matrices so others can reproduce the curve, of trusting the sky more than our priors by letting non-parametric reconstructions sketch the expansion before models are invited to explain it. Then the original puzzle stands resolved without losing its wonder, because a universe can be finite or infinite yet lack borders. It can grow everywhere at once without moving into anything, since the metric that defines distances evolves with energy density and pressure, and the evidence for that evolution now lives in microwave ripples, shear maps, electron tallies, merger hums, acoustic rulers, time-dilated light curves, and the steady drift of spectra that future instruments will watch unfold. So our path to an answer is the answer itself, a long measurement that begins with hydrogen forming and ends with horizons widening, where galaxies condense in dark halos, clusters breathe in hot plasma, voids swell in quiet black holes ring softly, photons redden gently, and all of it fits a single sentence written by general relativity in the language of an evolving scale factor. If there is a coda, it is this plain statement returned from 1,000 tests, that space needs no edge to expand because expansion is not motion through a room, but the changing yardstick of the room itself. A change we have weighed with candles, rulers, clocks, waves, and maps, until the only remaining shadows are where discovery lives, not where doubt about the edgeless stage survives.